All right, welcome back, everyone. I hope everyone is full of sugar and caffeine and ready for some rapid-fire topology. We're going to start off today, this session, which is going to be on comparisons with Ji Jian from University of Arizona, talking about autoencoder-enabled visualization of collections of Morse complex.
Hello, everyone. My name is Ji Xian, and today I'm going to present the autoencoder-aided visualization of collections of Morse complexes. So visualizing a large collection of Morse complexes is very challenging, and based on, given the successful application of deep learning in studying a large collection of images, we want to explore ways to utilize that power of deep learning in topological features of scientific data. So in this particular project, we use an autoencoder as a feature extractor to extract lower dimensional features from images of Morse complex. And more specifically, we use the boundary of two cells to represent the geometry of Morse complexes, and we feed those images of boundaries to autoencoders, and we project them using other projections to 2D to create visualizations to help us study the collections. And so I will show two examples of our visualization. The first one comes from a time-varying flow data set. We sample the slices from different x coordinates of the data set and compute the Morse complexes. And then we project those Morse complexes to a 256-dimensional space, and we use TSNE to project them down to 2D. So here is a TSNE projection. They are the same projection, but colored. The left is colored by the time, the right is colored by the x coordinates. And we can see that the projection groups those samples by their x coordinates. And for each x coordinates, they are organized in the sequential order. And we can also see some loop structures from the several x coordinates. And from our multiple runs of TSNE, we notice that the samples from the beginning of the flow, the earlier x, is more likely to form those loops in our TSNE projection. And the samples from the end of the flow, they are more likely to break those loops into several segments. The second example we will show is we sample the slices from 2 volumes of microscopy images, and we randomly sample 10,000 slices from those 2 volumes, and we project them from 512-dimensional space to 2D using PCA. And in this PCA plot, the x-axis is the complexity of the Morse complex. By that, I mean on the left side of the projection, we see Morse complexes tend to have many small features, while on the right side, they tend to have few large features. Well, the y-axis is basically encoding the location of the large feature. So from this plot, we learned that both volumes tend to have Morse complexes of many small features, but volume B is more likely to have a large feature than volume A. So in summary, we built this neural networks to we established that neural network can be used to study the image-based encoding of Morse complexes, and we can use those to study the geometry of Morse complexes. And in the future, we aim to extend this work to 3D, and we want to test some other encoding that have richer information. Also, we want to try the more complex network that doing the topological segmentation task. And finally, I want to thank my co-authors and the Department of Energy for the funding. And that concludes my presentation. Thank you.
Right on time, so we definitely have time for some questions. I'll start the ball rolling. So you're taking the arcs of the, and you're casting those into a binary image, right?
Yes.
So how sensitive is that to the resolution of the image, and have you sort of tested varying that resolution? And
In our study, we basically, there are two types of resolution. First, the resolution of the scalar field. That basically defines the size of feature you want to capture. And second, the resolution of image, which defines how, the resolution of image is more like a performance measure because larger image tends to be slower for the neural networks. So
if the resolution is low, wouldn't it not capture smaller features?
No, it doesn't. So you need sufficient resolution on both sides to capture really the feature you want. But in our study, we tried that mismatch. So for example, we used a larger sampling grade but smaller image. And it works. It works as an accelerator while it gave you some notion of detail in that sense.
All right, great. We have a question?
Okay, thank you for the presentation. So my question is that you said that you will plan to use more complex networks. So can you explain about the plan in more detail? What kind of model you're planning to use?
So right now, the autoencoder model is basically we want to form it as something that you can plug and switch. So for the study, we use ResNet as the encoder. For some simple data set. And we use, for the complex data set like the CRIME, we use something like HRNet. So on that side, I would advise you to choose a network with proper complexity for your data set, so to do the training and the projection.
Okay, thank you for the question. Can I do one more? Yeah. So I'm asking about, do you have any plan to use another autoencoder model, like variation autoencoder?
Oh, so that's a great question. We use a simple encoder, but we haven't tried on the other thing. But we believe those type of encoder which has some regularization on the latent space could give us something meaningful, but we didn't run those experiments with those models.
Thank you for the answer.
Sure.
Let's thank our speaker again. And up next, we have Florian Wetzels, who's going to present on a deformation-based edit distance for merge trees.
Do you know which number you are? Where is it? This one. Okay, thanks for the introduction and welcome to my talk. So it's about a deformation-based edit distance for merge trees. So quick motivation, why do we want to compare scalar fields through merge tree distances? So first we want to compare scalar fields because distance functions on them are important for clustering of ensemble data, periodicity detection in time-dependent data, or finding self-similarities. We want to compare them through merge tree distances because they capture topological similarity and the merge trees are much smaller than the original domains, so for performance reasons it's also better. We use tree edit distances because they are an established method to compare trees, which is very intuitive, flexible in regards to what kind of similarity you want to capture, and also efficiently to compute. And they are mapping based, and these mappings, they capture sequences of three types of edit operations, deletion of a node, which you can see in this example image here on the right, insertion, which is the invert operation of the deletion, and we can also relabel nodes or edges in the tree. But we cannot simply apply them to merge trees because we have an example here. In the middle tree, if we delete the smallest maximum, we get the tree on the right. This is not really a meaningful merge tree because there's an inner node of degree 1, which is not allowed. And what we actually want to have as a result is the tree on the right with some kind of continuous delete. And how to tackle this problem? There have been several attempts, so we could simply ignore it, but then we get a poor quality mapping and also a poor quality distance measure. And what has usually been done is to work on branch decomposition trees instead. But this introduces stability problems because of some hierarchical constraints in a fixed branch decomposition. And this could, for example, lead to false clusters being found where there are none. So in this distance matrix in this image here on the right, these clusters that you can see there, they shouldn't be there. In a previous paper, we fixed this by optimizing over all possible branch decompositions. But this came at the cost of an increased complexity of n to the 4 and especially losing the metric property. But on the same data set, we do not find these false clusters. And in this paper, we introduced a path mapping distance, which completely skips this route via branch decompositions and implements these continuous operations directly. And it's also branch decomposition independent. It has the same increased complexity as the branch mapping distance, but it is a metric. And here we can see we get the same correct results as with the branch mapping distance. What this distance actually is an added distance that is based on the added operations continuous deletion, continuous insertion of an arc, and the relabel operations, which are basically stretching or shrinking arcs in the merge tree. And this is actually equivalent to the transformation of deformation retractions on merge trees as topological objects. In our paper, what we do is we define this added distance, define the equivalent mapping model, and then derive an algorithm from that. And we also provide an open source implementation, which is available on GitHub. And currently, our code is pending for integration into the topology toolkit, where it will hopefully soon be available. Yeah. Thank you.
Thank you. That's great work. While people are thinking about their questions, I'll get started. So the edits that you're doing are sort of this very intuitive, sort of moving from one merge tree to another. Have you ever thought about whether or not that could lead directly to a visualization approach to show sort of how these two trees are different in sort of
yes,
the tree sense?
This is basically, so at the moment we are doing a very basic integration into the TTK, but for the future we want to combine this with the Berry Center and a geodesic approach that is already in TTK with another merge tree distance. And when we combine them, we can actually do exactly this. Then we can use the visualization approach that's already in TTK to showcase this transformation.
Right, yeah. Cool. All right, any other questions? All right, if not, in the sake of time, we could thank both of our speakers.
All right, ready? Okay, so my name is Christoph Gard from the University of Kaiserslautern. I welcome you to the second session in this session, I guess, on bivariate and vector data. The first talk is about reduced connectivity for local bilinear Jacobi sets, given by Daniel Klötze. Go ahead.
Yes, hello everybody. So today's talk is about reduced connectivity for local bilinear Jacobi sets. This is a joint work between the University of Stuttgart, Linköping University, and the University of Utah. So let's jump directly into it with the definition of Jacobi sets. The Jacobi set is a topological descriptor that captures gradient alignments among multiple Morse functions. In a two-dimensional case, it can be defined via the set of points x in M, where the cross product of the gradients of f and g equals 0. The original computation method by Edelsbrunner and al., or Edelsbrunner and Harrer, was extended by my colleagues and me to the local bilinear computation of Jacobi sets. This improved the geometry while maintaining the topology of the piecewise linear method. But it came with a downside, namely the light red quadrilateral on the right, which you can see, where you have overlapping line segments. This, in the future, we will also see as some higher dimensional simplex. How does this look like in a real data set, in an analytic data set? Well, we have the following data set given by the function values of f and g as contour lines in blue and red, and the analytic Jacobi set in black. In the local bilinear method, you can clearly see, especially in the zoom-in areas, that there are lots of overlapping line segments. So our main research question was how to improve this connectivity of the local bilinear method. Therefore, we stated the following 4 design goals. First of all, we wanted to preserve the topology again, meaning we wanted to find a homotopy equivalent representation. Secondly, the geometrical configuration done by the Jacobi set points and their positions should be preserved. The third point was to uphold the even degree lemma. And finally, we wanted to have a deterministic algorithm in the end. So how did we achieve this? Our new connectivity method comes in 2 steps. Starting again with our toy example from before, where we had this overlapping line segments, we start with the simplicial collapse. In the following, you can see some way of the elementary collapses of one simplicial collapse of this higher dimensional simplex. Important to point out, this is not unique, but we get one vertex in the bottom right, which is connected to all the other vertices of the higher dimensional simplex. In the second step, we take this one vertex, split it, and leave one vertex at place, and shift the other vertex to the barycenter of the surrounding vertices. All these methods were now homotopy equivalent, so therefore this is also some part of the main proof of our homotopy equivalence proof of the paper. So how did we achieve this algorithmically? Starting with the standard connectivity, it's quite easy. We just delete all the edges which are overlapping of these higher dimensional simplex. Then we introduce the barycentric point of the vertices, and we connect this point to all the other vertices of the higher dimensional simplex. And this is already the reduced connectivity, at least for this toy example for this talk. And like we said before already, this is homotopy equivalent to the local bilinear method. And now we can look again at the example from the beginning, where we have our analytic data set on the left and our data and the reduced connectivity on the right. Especially in the zoomed-in areas, you can see that these long redundant line segments on the top right get reduced to this hourglass-like structure. But also structures where there are no crossings don't change, like this triangle on the bottom left. This ends my talk about the reduced connectivity for local bilinear Jacobi sets, and I want to thank you all for your attention and for the possibility to being part of TopoInVis 2022.
Are there any questions? If not, I will get us started. So Jacobi sets are not known for their numerical robustness, right? So if you add a little bit of noise, the structure changes dramatically. So does your method maybe have the potential to sort of act as a smoothing type method for noisy Jacobi set results?
No, not really, because it has exactly the same topology as the piecewise linear method, and thereby the Jacobi set, which is in the piecewise linear method, I would say, yes, not very good in terms of uncertainties. It's also not good in our method because we don't really reduce the main structures. It gives a better geometrical representation, which comes through the local bilinear method, and these overlapping line segments, they get reduced with this method.
All right. Any other questions? If that's not the case, then let's thank the speaker again. Okay, and the next presentation is going to be a virtual one. It's about Jacobi set-driven search for flexible fiber surface extraction by Mohit Sharma.
Hi, my name is Mohit Sharma, and I'll present our paper titled as Jacobi set-driven search for flexible fiber surface extraction. Given a bivariate field, we can plot its two-dimensional continuous histogram known as continuous scatter plot and select an interesting region in the range space using a control polygon. The control polygon maps to a fiber surface in the spatial domain, which is bivariate counterpart of an isosurface. Jacobi edges are the bivariate alternative of critical points. The Jacobi edges marked with cross are close to the fiber surface to be extracted. The Jacobi fiber surfaces corresponding to Jacobi edges segment the domain into regions that have same fiber topology. They help to limit the search for fiber surface components to small regions in the domain. Based on this intuition, we present a 4-step algorithm to extract the fiber surface corresponding to a given control polygon edge UV. In the first step, relevant Jacobi edges are found out by computing intersections of the line extended through UV with the Jacobi set. A directed search is initiated from each relevant Jacobi edge towards UV to identify the seed tetrahedra. From each of the seeds, a BFS is initiated to extract all the tetrahedra containing the output fiber surface component. The extracted tetrahedra are then passed to TTK for fiber surface computation. We validate our results via qualitative comparison with fiber surfaces computed using TTK and comparing the total number of tetrahedra containing the fiber surface against an exhaustive search. Time taken to compute the Jacobi intersections directly depends on the total number of Jacobi edges. The algorithm performs better for the dataset having fewer number of Jacobi edges compared to the domain size. The algorithm performs better than non-octree version of TTK for the cases having a smaller number of Jacobi edges compared to the domain size. Our method facilitates flexible computation of individual fiber surface components. The intersected Jacobi edges can be visualized within the domain. Interestingly, the intersecting Jacobi edges form clusters near the expected feature. A particular Jacobi edge can be selected interactively from a cluster to extract the corresponding fiber surface component. For ethane diol molecule, the algorithm is able to extract one oxygen atom, one carbon atom, and one component for each of the bonds. With this, I would like to conclude my talk. In future, we plan to improve the algorithm's performance using space division techniques and explore methods to avoid the user interaction for interesting Jacobi edge selection. If you have any questions, please ask.
Your search.
To hear the question?
No, I could not hear it.
Oh no. Yeah, I think you best use this microphone. Can you hear us okay when I talk? Okay.
Yes, I can.
So let's repeat the question.
So I think what you're doing is related to what I used to call path seeds. Sorry, this is Hamish Carr. And in that, we searched outwards from the critical points in the contour tree to seed a search for the surfaces we're interested in. So I think what you're doing is related to that, and I'm interested in details of how you make sure that you direct your search in the correct direction in the space.
Yes, yeah, sure. It is exactly related to the univariate analogous part. And how we direct is, so I imagine the control polygon inside a range space and I extend a line through that control polygon. So it's a bit technical. And on that line, I figure out which tetrahedra are intersecting with that particular line inside range space. And then I keep on moving towards the control polygon edge. just on that line.
So the problem I see with that is that if there are two directions in the space that you can travel, which will take you to the intersection of that control polygon, you will extract both components, whereas you might only want to extract one of the components. So I think at some point you need to store an additional piece of information if you genuinely want to treat the components as individual surfaces.
Yes, so yeah, that is one thing. So by default, I don't know which component I'm going to extract if I'm just starting.
Now it makes sense. Now it makes sense. Thank you very much.
All right, any more questions? That's not the case, then let's thank the speaker again. Thank you, Moit. Okay, and the third presentation of this session is about discussion and visualization of distinguished hyperbolic trajectories as a generalization of critical points, given by Roxana Bujak.
Hello, everybody. My name is Roxana Bujak, and I'm excited to be here and have the chance to talk to you about my paper, Discussion and Visualization of Distinguished Hyperbolic Trajectories as a Generalization of Critical Points to 2D time-dependent flow. 4 minutes is not a long time, so I hope I would just have enough time to tell you what it is we're trying to solve here. And the problem that we're dealing with is that the classical flow topology, as we know it, to visualize steady vector fields, does not really translate to time-dependent flow. It has already been pointed out a long time ago by Perry and Chong in '93 that instantaneous streamlines, which are the foundation of the classical flow topology, have found considerable use, even though they are not Galilean invariant and appear to lose physical meaning if the flow is unsteady. In a recent state-of-the-art report, we have collected all the different mathematical properties that have been considered by authors as criteria for a method to be physically meaningful and to serve as a physically meaningful generalization for the classical vector field topology. And for this paper here, we focused on the three important ones. First one is the method has to coincide with the steady topology if the input field happens to be steady. It has to be Lagrangian invariant, so that means the features that we extract have to be tangent to the flow, so the particles cannot cross the boundaries that are formed. And the method has to be objective. That means it has to be independent of the frame of reference of the observer. The time is already half up. Well, so what we did not look at in this state-of-the-art report was distinguished hyperbolic trajectories, even though they are a very promising tool to actually satisfy these three properties. Please press pause, read this slide carefully if you have time. Better, read the paper by Ida et al. Explains it really nicely. And the number one contribution of the paper that I'm talking about here in this talk is we take the concept of DHTs and analyze, do they satisfy the three properties that we need for physical meaning? So are they Lagrangian objective, and are they actually a generalization of the critical points of the classic flow topology? And I have no time to talk about this. Read the paper. You will be surprised. You think they do? Maybe. Read the paper. Contribution number 2 of this paper is for the visualization of the DHTs. Here in this video, we see a saddle, steady saddle, that is just rotated along this circle with increasing speed. And it would be really nice, once we have detected, oh, this is actually the DHT, that we could see it in the same way as the classical vector field topology. There is a transformation for the detection in the DHTs that makes everything extremely steady, and we first thought that would be a good choice. But that actually violates the desired property number 1, because it can change the type of critical points. Yeah, so contribution number 2 of this paper is we derive a transform that is a little less invasive than the one that is used to detect the DHTs, so that it satisfies all three properties to guarantee physical meaning. Yeah, go, read the paper. Read the paper, read the paper. Bye.
Can we, oh, okay. Can you hear us now?
Yes.
Awesome, awesome. So I read the paper. Since there are no other questions, let me go ahead and begin with one. It seems like you're advocating for DHT sort of as a generalization for classical vector fields, just to give a spoiler to the audience before they read the paper. But so you also comment about how numerically difficult it is to actually extract them. So is this, do you think at the end of the day they will be practically useful?
That is a hard one. I would say, as of my current implementation, I doubt that. But, I mean, I'm not the best programmer in the world, and the science, I don't think, is at its end yet. I think there are still ways in which they can be extracted in a more robust way. But, yeah, really, I have to admit, I was not really able to get a robust way to detect them yet.
All right. Any other questions? If not, I have one more. Looking at your visualizations, did you consider using an unsteady texture-based technique to visualize the unsteady flow? Something like, I don't know, UF-Lick or Lagrangian Eulerian advection or such techniques?
No, not at all. The idea was really to make the visualization as intuitive as possible to somebody who is used to the classical steady topology. So I have not considered any of those. I don't know. It might be an idea to consider that, but it's really a path that I have not thought about at all. Yeah, by the way, when I say I'm not the best programmer in the world, I might not even be in the top 10.
All right. If there are no other questions, then let's thank Roxana again. Thank you. Okay, and just like that, the session is over and we move on to the next session, the analytics session. And we start out with a virtual presentation about Classmate, a matrix of small multiples to analyze the topology of multi-class, multidimensional data. And the presentation is virtually given by Michael Opetit.
Classmate, a matrix of small multiples to analyze the topology of multi-class, multidimensional data. I'm Michael Opetit, and I will present this work, which is joint work with Ahmed Ali, Abdelkader Bagag, and Halima Betsmail. We are all working at Qatar Computing Research Institute. Considering exploratory analysis of multidimensional label data, what is the class topology in the data space? Our class is compact, split, separated, adjacent, nested, overlapped. We can visualize data using projections, like TA or UMAP, or we can use scatterplot matrix. All these tools reduce dimensionality, but they are confusing about classes. There are distortions like false neighbors, missed neighbors, and it is difficult to focus on a single or pairs of classes. There are two challenges. One is about multidimensional, and the second one is about multiclass. There are general approach for multidimensional data. The very well-known one is to first project the data using dimensional reduction techniques, PCA, Disney, etc., and then performing the topological analysis in the head of the user. The second approach is to first perform the topological analysis in the multidimensional space using some topological modeling techniques, and then visualize the result of this analysis using, for instance, persistence diagrams, and let the user interpret this visualization. So these two approaches are well known, but what is new is an approach specific for multi-class data. And that's what we present here. This tool is called Classmate, and in this tool we can isolate single classes along the diagonal of this matrix and isolate pairs of classes off diagonal. So it is a representation which is very similar to the scatterplot matrix, except it is focused on classes and pairs of classes instead of original dimensions. Classmate helps navigate across classes. For instance, we can explore all views related to one class. We can get the other class that contributes to a pattern with the first class. We can spot the pattern and find contributing classes. In the visualization first, then topological analysis, we can, for instance, use scatter plots where the axis, because now they are not specified like in Splom, they are not specified as axis from the original space. We have to specify the axis given the classes. So on the diagonal, we use PCA, principal component analysis, for single class. And off diagonal, we use LDA, linear discriminant analysis of two classes that are represented in that specific cell at the crossing of the row and column of the matrix. For the TAV approach, we can use persistence diagram, and here we propose a new way to visualize persistence diagram for pairs of classes. So on the diagonal, you have standard persistence diagram focused on only the points of a single class. And off diagonal, you first report the persistence diagram of single class to give a context, and then you represent on top of it the persistence diagram of the union of the two classes. And as you can see in some cases, does not correspond to the initial data. So when the union of class does not correspond to the single class persistence diagram, that means there is some interference between the class which change the topology of the union of the two classes. So in short, the next step are design interactive version of Classmate to allow more selection across rows and columns, evaluation with end users, and regarding the two-class persistence diagram, design guidelines to interpret these two-class persistence diagram. Thank you for your attention, and please check our paper for more details and usage scenario.
Hello, can you hear us?
Hello, yes, I can hear you.
All right, are there questions? Let me start off with a question. So can you give us some insight on what forms of interaction you would see for Classmate?
The interaction can be about selecting points, so selecting class, especially when you have in a single class, you have two clusters, for instance, or several clusters, you want to separate these clusters into individual classes. So you could modify the classification actually, based on what you see in the plot. That could be one way to interact with this sort of plot. Yeah, that's the main thing I thought about.
All right. Any other questions? Pardon me? Oh, sorry, this is not a question, but we are asking the tech staff to remove the mouse from your image. It's over your nose. Okay, so, there's a question.
Can you hear me?
Use this microphone here.
I think this one works. Okay. No? Oh, can you hear me?
Yes.
Oh, okay, cool. It works. I was curious, in your in the scatter plot similar view you have, the diagonal were PCA. The off diagonal, are they also PCA?
No, they are on the...
Oh, LDA, right?
Yes, linear discriminant analysis.
I'm actually quite curious because it seems like that plot is independent of the plot of the persistent diagrams. Is there a way to sort of connect them?
Actually, these two plots come from two different data sets.
Oh, okay.
But you could imagine to have actually, I did not try that. We could use the same data set and visualize them in the different ways. Yes, in this paper, I focus on a very typical data set, especially for the persistent diagram. I use very toy data where you have nested spheres, nested interlaced cycles, etc., to check the very basic pattern we could see with these persistent diagrams, especially with the union of classes. So that's why I use very simple data on that case. But I did not try to visualize the same data set with the two different approaches. Yes, that's a good idea.
I guess it will be interesting because it feels like one encoding is sort of visualizing the geometry. The other encoding is just visualize the topology, and we know they are connected to each other. So seems like amazing future work you can do if you can connect those two visualizations. Yeah.
Very good idea, yes. Thank you.
Thank you.
All right, let's thank Michael again.
Thank you very much. Bye.
Thank you, bye-bye. Okay, and this gets us to the second talk in analytics in presence. It's about untangling force-directed layouts using persistent homology. The talk will be given by Bhavana Dopalapudi.
Hello everyone, I'm Bhavana Dopalapudi from University of South Florida, and today I'll be presenting untangling force-directed layouts using persistent homology. This work is in collaboration with Bei Wang and Paul Rosen. Force-directed layouts are popular for representing node link diagrams because they're simple, fast, and aesthetically pleasing. But one of the major issues with force-directed layout is their lack of direct consideration for global structure. This often results in overlap of unrelated structures and visual cluster. In our paper, we use persistent homology-based framework to provide better initialization and to interactively untangle the overlapping structures of the graph. Our persistent homology-based framework utilizes edge filtration to extract the 0 and 1-dimensional topological features in the form of 0-dimensional connected components and 1-dimensional cycles. The top 2 rows represent the 0-dimensional connected components where a few nodes are connected by edges. The bottom 2 figures represent the 1-dimensional cycles. To efficiently extract these features, we use maximal spanning tree, whose construct is similar to that of a minimal spanning tree, except it selects the highest weighted edges first. The maximal spanning tree extraction resembles the 0-dimensional components, and the non-spanning tree edges can be used to extract the cycle. The example in the right, the gray represents the maximal spanning tree component, and the non-spanning tree edges in the red can be utilized to extract the 1-dimensional cycle. In general, D3 uses random node positions to initialize the layout. We improve this approach by utilizing a tree structure, either layered or radial. The result of that modification is twofold. First, it improves the rate of convergence. For almost all data sets, our approach converged faster than the random layout. The visualizations in the blue show that. The top row of visualizations are those produced by the random layout, and the bottom 2 rows of visualizations are those produced by our layout. It can be observed that as early as 5 iterations produce a well-defined structure with our approach, whereas the random layout takes almost 25 iterations. Our approach also converges graphs to better quality layouts. When we see at the visualizations on the green box, where the top row represents the visualizations produced by random layout, and the bottom 2 rows represents the visualizations produced by our approach, it can be observed that after 300 iterations, the clusters formed by the random layout are loosely formed, whereas the clusters formed by our approach are tightly formed and well-defined. Here, we provide some more examples where our approach untangles the cluttered visualizations produced by random approach represented on the top. We also provide users with interaction capabilities of 1-dimensional features in the form of highlighting the cycle and adding cycle emphasizing forces to the graph layout. The highlighting is activated when user hovers their mouse on the barcode visualization, and the force is added when the bar is clicked upon. Our cycle emphasizing forces apply elliptical force to the nodes of generator of the cycle. The elliptical force is added in such a way that it untangles any knotted structures. Here, we show some more examples where applying forces to the 1-dimensional persistent features result in better layouts and well-defined cycle structures when compared to the cluttered visualizations produced by random layout on the top row. For graphs with multiple cycles, this animation provides context when switching between different cycle emphasizing forces. We provide an easy way to improve force-directed layouts by providing better initial positions that reveal hidden, clustered, or overlapping structures. We also provide new forms of interaction on one-dimensional components. Our approach is relatively lightweight, and the overhead is relatively low when compared to force calculations. Thank you, and any questions?
There's a bit of time for questions. So let me go ahead and start. In the paper, you write a little bit about evaluating your layouts. Can you elaborate a little bit on that?
Yeah, we evaluated our using calculating metrics such as co-ranking, edge crossing, and average iteration time. And those metrics show that our approach performs better when compared to the random approach used by D3.
All right. And how stable is sort of your initialization technique if the data set changes slightly? So if you get additional edges, will you get a dramatically different result? So,
can you repeat it?
Oh, sure. So if your initial graph changes a little bit, so you get an additional edge or so, how much does that influence the outcome of your layouting algorithm?
It just untangles the overlapping structures, and we get to understand better layout of the graph and analyzing what the structure of the nodes are.
All right.
We just position the initial node. We just position the nodes in a different way rather than just randomly.
Yep. All right. Any other questions? That's not the case. Then let's thank all the speakers again.
All right, for our next session, hello everyone. I'm Federico Juricic from Clemson University. We are going to switch soon to the session application. And for this session, we will have our first talk about exploring cyclone evolution with hierarchical features by Emma Nilsson, whenever you want.
Yes. Hi, I'm Emma Nilsson, a PhD student at Linköping University, presenting our paper today. So our collaboration partners research multi-centered extratropical cyclones, which are hard to identify and track. So their current methods suffer from slow execution, that they are tailored to specific cyclones or regions on the Earth, and that they require a lot of parameter tuning, which is a tedious process for the scientists. Also, cyclones can form from really shallow pressure minima, which not all cyclone methods can detect. And the accuracy of the tracks is really important for the scientists because they base their entire analysis on them. So in our approach, we wanted to be able to detect these multi-centered cyclones while still being efficient and robust and give an opportunity to explore multiple parameters at the same time. So this is an overview of our framework. As input, we have time-dependent pressure fields, and on these fields, we track minima using gradient tracking. We also calculate the merge tree, and on the merge tree, we define a feature characterization. And this is hierarchical in nature and sorts minima into nested separate groups. Finally, we derive feature tracks by inheriting the connectivity from the gradient tracking. And here you can see on the left visualization of the nested tracking graph of our features, and on the right the spatial embedding of the cyclone tracks. So as I earlier said, we wanted to use hierarchical features. A classic example of this is sublevel sets. So for sublevel sets, if you have an ISO value, you get a set of components, right? And when you increase the ISO value, the lower ISO value components will be nested into the higher ISO value components. And this yields a nesting hierarchy. But the problem with this is that it's a global threshold, and we need something local to address the challenges in the application. Therefore, we define crown components. So crown components are defined on the merge tree, and you take an offset called the crown height from the deepest minimum within a branch, and then as you increase the crown height, you can see that the lower crown height components will be nested into the higher crown height components. And you can also see that all minima will be long to one crown component. And this gives a flexible feature characterization for the scientists. So if you go back to the visualization, you can now explore these hierarchical features in the abstract tracking graph, and the scientists can determine whether the groupings seem reasonable, and they can also explore them in the spatial embedding. Finally, we compared our results with the IMELAST community effort for cyclone tracking. And as you can see in the upper left embedding, we can detect merge and split events that not all pressure-based cyclone tracking methods can do. And therefore, our approach is flexible and modular while still supporting parameter exploration quickly, without much parameter tuning. Thank you.
Thank you very much. There are questions. Well, let me go first. Are you planning to, or like thinking of using the same approach for tracking other type of features rather than cyclone, or have you ever considered that?
Yes, so if you listen to Farhan's talk later in the session, you will see how we applied ground components to fMRI data.
Gotcha. I also, well, sorry.
Oh, okay. I was curious, in your new framework, there are different thresholds for sort of different branches. How are those thresholds determined? Are they coming from domain scientists, or there's a specific way to kind of adaptive chose, those thresholds?
We have used domain science knowledge usually for the thresholds, and there has been no adaptive learning or anything like that to determine the thresholds.
Okay, thanks.
Thank you.
Any other question? All right, then I propose to switch to the next talk, which is going to be about towards benchmark data generation for feature tracking in scalar field, and it will still be about, like, from Emma Nilsson.
No. Okay, wait a bit. No, right?
Is it that one?
Yeah. Sorry about that. Okay, so it's still me, and now I'm presenting my next paper. And in this work, we were motivated by that there are a lot of different feature tracking methods, and feature tracking is a very common task in visualization. And mostly these methods are evaluated using qualitative visual analysis of the tracks. But we wanted to come up with a way to compare these methods with quantitative measures and be able to determine what method should be used for what features. And we also wanted to be able to test our methods during development with other methods, but also previous iteration of our own methods. And to do this, we decided to create a benchmark data generator, and we had to ask ourselves 3 questions. What features should we look at? How should we propagate these features? And how should we define feature events? And for the first question, we decided to look at point-based features, such as critical points or level sets. And remember that level sets enclose at least one critical point, even though they are a region-based feature. So we simulated a point cloud through a domain, and we propagated the features throughout vector fields, and you can choose a simple or complex vector field. But as I said before, we needed to define features. And we started by saying, okay, each feature should have a value at the point, and the value should extend from the point. And we decided that each point carries a Gaussian function. And then to go from points to features, we had that you could evaluate these Gaussian functions in different ways. So here we have taking the maximum, thresholding the maximum, or summing the Gaussians. And if you then evaluate these function combinations, you can derive scalar fields. And on the right, you have spatial embeddings of 2 scalar fields, one for point-based and one for region-based features. I also said that we needed to define feature events, such as merge, split, birth, and death. And to do this, we decided to use mathematical analytical expressions that are quick to evaluate, so we stay efficient. And we encode these events in correspondence matrices. And from the correspondence matrices, we can derive a tracking graph. So in this slide, I show an example of thresholded maxed Gaussians. And in the tracking graph, you can see that we have both features that are born, that die, and that merge and split over time. Like I said, we wanted to evaluate tracking methods, right? So we came up with an event-based evaluation where we compare the correspondence matrices in each time step and check that the same features are involved in the same feature event. And we also defined 3 measures. So precision measures how many feature events the algorithm detects correctly. Recall how many feature events the algorithm detects from the benchmark data, while accuracy combines them both. Finally, I want to say that this is just the first step. There are many ways you can create features from points and many functions you could use. And there's also some work to be done on the evaluation procedure. We currently look time step by time step, so we penalize if an event happens in a different time step but is still correct. So with this work, we wanted to open a conversation on how we can use benchmark data in feature tracking and incorporate it during research. Thank you.
Thank you very much. Questions? I'm very curious about the last thing that you mentioned. You said about the evaluation, how you're currently evaluating the accuracy based on specific time step, right? Are you considering to introduce also like other type of evaluation, like in maybe coming from like object tracking field where they try to do similar things? They try to like track object and they have to evaluate how much like the tracking was done, even if the identification doesn't happen in a specific time step.
Yeah, so our current idea is that we will have sort of like a window around a time step, and if an event happens within that window, we will sort of scale depending on how far away it is from the time step the ground truth says. I didn't really actually hear the end of your question though, but I hope that answered it decently.
Perfect answer. Thank you. There is a question.
Okay, so I think first of all, does this work? Yeah. No?
I'm not sure it is.
Okay, good. So I wonder what's the impact of your assumption of Gaussian? So have you compared them to any kind of physical simulated data of flying loss?
So assuming Gaussians is that's sort of why we have all these different combinations, because if you sum Gaussians, you get something that looks very natural to physical simulations. We have talked about, for example, the superposition principle that is kind of common in physical simulations. But the problem with summing Gaussians is that there's no analytical expression that can guarantee that a merge or split has happened between unimodal, like when you go from bimodal to unimodal. So that's why we started looking at taking the maximum of the Gaussians, and that gives you a very strict merge and split definitions, but instead you have a discontinuity where you have that one Gaussian is higher than the other. So yeah, that's kind of why it's future work, I would say. Thank you.
Thank you very much. And let's thank our speaker again. And so the next presentation is an online presentation. It's subject-specific brain activity analysis in fMRI data using merge trees by Farhan Rashid.
I am Farhan, and welcome to our talk on subject-specific brain activity analysis in fMRI data using merge trees. Functional MRI is widely used to examine activations in the brain. It works in effect that the brain activity is coupled with changes related to the cerebral blood flow. However, analyzing fMRI data is challenging because the real-world measurement of the signal is a complicated mixture of true stimuli and noise which can arise from many sources. Current fMRI analysis approaches require extensive pre-processing steps to reduce the noise factors. They also require template registration to get predefined regions. Our aim is to design an approach that avoids these pre-processing steps and work directly on the raw data. The data we work on is a time series of scalar fields representing fMRI observations. Each participant was scanned for about 25 minutes while performing 4 different tasks. The time steps are labeled according to the underlying tasks. In this work, we present a merge tree-based method that extracts highly active subject-specific regions and allow tracking these regions through time. For sake of simplicity, we illustrate our method for one-dimensional case. Given a one-dimensional function, we compute its merge tree as it provides a good summary of scalar dataset. Here we are only interested in maxima because the highly active regions are associated with high intensity values. Based on certain relative value difference, we group maxima that belong to the same cluster. This step makes our feature robust to noise. We obtain a feature vector by collecting these regions into a vector form. For our dataset, we extract a series of merge trees from all time points. In order to establish a correspondence between these merge trees, we utilize the idea of geometry-aware comparison based on a subject-specific reference brane. This reference brane is computed by combining maxima from all time points. We compute its merge tree followed by extracting its regions, similarly as we performed for one-dimensional case. This reference brane introduces a global index set that provides a good mean of tracking activation regions. Computing feature vectors from all time points and stacking them on top of each other results into a feature matrix, where each row corresponds to a single time point and a column represents the activation region. To get an overview of temporal development, we reduce its dimensionality using TSNE and visualize in the form of scatter plot. Each dot represents the single time point colored respective to the task. To further understand the temporal evolution of the brain activity, we provide distance plots showing the deviation of each time point from the reference brane and the pairwise distance across the time steps. The same feature matrix is used for the connectivity analysis using a code diagram. Two regions are connected through a ribbon if there is a significant correlation with each other. The visualization provides interactive capabilities for selecting and filtering regions. The results from other participants shows similar patterns. In conclusion, we extract subject-specific activation regions. We introduce a reference brane to find geometry-aware comparison between merge trees. By this, we generate a feature matrix which can be used for both temporal and spatial correlations.
Hello, Farhan, can you hear us? I would say that is a no. Farhan, can you hear us well?
Yeah, I can hear you. You guys can hear me?
Fantastic. There are questions. I can start with a question. Do you guys have been able to propose your tour already to domain scientists and having them playing with it? And if yes, what did they say?
No, we haven't got any feedback, or it wasn't any domain scientist in the study. But we do ask some of the colleagues, the domain scientists, to get an intuition how it would work. But they said that yeah, the results seems to be expected.
Sounds good. Any other question? Well, since we have time, I do have a follow-up question. It kind of feels that like you guys you're starting from a reference image in your tool, and from there you compute like a merge tree, and then you go on comparing with all the other merge tree. And I was wondering while reading your paper if that was like a decision that you made, or if you ever considered starting directly to creating a reference merge tree or some sort of a representation of all the merge trees that is computed a posteriori rather than starting from the image.
Yeah, of course, there were other possibilities like this. The comparison always be a two-step. Like first, you need to find the labels of each maxima points. Then you need to a metric to compare them. But the decision here to give a label at each time step or to make it consistent. So the idea to generate a reference brain is that so we can combine activations from all the time points and extracting the merge tree afterward, and not just grouping the leaves that were before.
Got it. Thank you very much, Farhan.
You're welcome.
And let's thank again all the speakers in this session. This was the last talk of the application session. And with this, we are stepping into the 1-minute lightning talk. So this will be like very fast lightning talk of 1 minute each. And the first one will be lightning talk by Raghavendra Sridhar Murthy. Yes, you're here. Awesome.
Hi everyone, I'm Raghavendra, a PhD student at IISc, and I'll talk about comparative analysis of topological structures. Why compare topological structures? Scalar fields are real-valued functions like electron density in this example, arising from scientific measurements. Comparing them is a fundamental step in any meaningful analysis, and since point-wise comparisons are prone to instabilities and are not invariant to transformations like rotation, we first build a topological structure, which is a combinatorial abstraction like merge trees or graphs, and we have a proven method to simplify these structures via topological simplification to remove noise. Once we have simplified structures, we can compare them and gain useful insights about the data. So it's a challenge to find measures which compare topological structures coming with great theoretical guarantees, efficient algorithms, and also easy to interpret. There is also a lack of local comparison measures and comparison measures based on complex-based structures. So we want to design methods to compare scalar fields by comparing topological structures. We want these methods to be intuitive, useful, have proven theoretical properties, and also have efficient algorithms. So we provide two comparison measures, one local and global, MTED and LMTED, which are metrics with efficient algorithms. We provide a lot of applications like symmetry and periodicity detection, feature tracking, and analysis of effects of topological compression, to name a few. In summary, we present methods to facilitate global and local comparison of scalar fields with efficient algorithms and applications. In future, we want to come up with a generic framework which has all these measures, further analysis of theoretical properties, and also we want to have comparative measures for other structures. Thank you.
Thank you very much, Raghavendra. There is no Q&A during this session, but I strongly encourage you to reach out to all our speakers like offline and ask them a question about their work. Next lightning talk is by Tananun Sonde by Wood. I don't know if you're here. I hope so.
Hi, I'm Tan. In this video, I'll give a brief statement of the key ideas of my research, Scalable Topological Framework for Machine Learning. Topological Data Analysis, or TDA, offers insights into the structure of high-dimensional noisy data. TDA characterizes the topological features in terms of dimensions. A zero-dimensional feature is called a connected component. A one-dimensional feature is called a cycle. These features can be generalized to any dimension. However, TDA is not scalable to large and dense networks. An additional problem is the notion of proximity required in machine learning. What sustained distance is a promising choice to quantify distance between network topologies. It has sound theoretical basis with many successful applications in machine learning. However, what sustained distance has a very high computational complexity and requires the use of approximation algorithms. My research proposes utilizing a one skeleton, which is a representation of a graph in a plane. In the one skeleton, there are only connected components and cycles. There are no high-dimensional features, which are nonetheless rarely used since they are hard to visualize and interpret. Importantly, topology in one skeleton can be computed exactly and efficiently. In addition, what sustained distance between one skeletons has a closed-form solution. Similarly, what sustained barycenter, which is the mean under the what sustained distance, also has a closed-form solution. As a result, numerical computation of the what sustained distance in barycenter can be computed very efficiently. The first application to the topological framework is regression, by topologically integrating fMRI and dMRI brain networks. Second application is clustering to maintain the simplicity, scalability, and effectiveness of the classic k-means algorithm, which is not possible using conventional TDA approaches. We recently proposed an efficient vector representation for one skeleton that is discriminative and highly interpretable for classification tasks.
Thank you very much. And our last lightning talk of the session in from Hee-Yoon Jeong will be set up in a second.
Okay, hello. This is Hyun-Jun, a first-year PhD student from Seoul National University. Hello. So today, I would like to talk about trust. Let's assume that you're analyzing some kind of data. You'll probably select a certain technique to use. For example, if you investigate some kind of high-dimensional data, you might exploit dimensional reduction or parallel coordinates. This means that you trust the technique's reliability. Without such trust, you will select an alternative technique that seems to be more trustworthy. Now, let's think about the opposite situation. You want to check the reliability of a novel technique you made. Then a certain data set should be chosen. You will check whether the structure of the data that you already know is well revealed by the technique or not. Here, you believe that the data truly has such a structure. These sorts of trusts are useful. However, they can also lead us to incorrect conclusions. For example, who knows dimensional reduction perfectly represents high-dimensional space? So during my master's degree, I threw questions about such common trusts, which we call assumptions, in the field of high-dimensional data and cluster analysis. I developed a tool that examines whether such assumptions are true or false in advance. I made techniques that better match the common assumptions and implemented a system that can elevate the problem when there is no way to escape from violating the assumptions. Please reach me if you have an interest or question about my works. Also, it's in my website. Also, I'm seeking an internship opportunity next summer. If you're looking for a passionate student to work with or knows someone who does, please let me know. Okay, thank you.
Thank you very much. And this concludes our lightning talk session. And with this, I will pass the mic to the workshop organizers.
Okay, thank you everybody for being here. I think it's been a really great day. I hope everyone's enjoyed our program. I have the honor of doing the best part, which is doing the awards. So the awards for this, for best papers, we had a committee of 3 members. We handed the committee the top ranked papers by our IPC, and they came up with 2 honorable mentions and a best paper. And so I will jump right into it because we're already at 5 o'clock. So first, our first honorable mention is for a subject-specific brain activity analysis in fMRI data using merge trees. And if one or more of the authors would like to come up, we have certificates for you. Okay. Next up for our second honorable mention. One goes to reduced connectivity for local bilinear Jacobi sets. And again, co-author. Look at a ton of them. This is great. I had a really thick stack I had to print for all of you. There you go. And there are enough copies for all of your co-authors, okay? You have to figure out how to get them to everybody. Congratulations. Okay. And now for the best of the best. Our best paper is a deformation edit distance for merge trees. Congratulations, guys. Thank you. Okay, so that pretty much wraps it up. First thing I want to do before we dismiss everyone is to remind you that we do have this informal get-together tonight. For those who want to walk over or take the tram together, we're going to meet in the lobby at around 5:30, so please join us there, or you can meet us at the restaurant. We do have a reservation under the group name TopoInVis. And a big thanks to everyone involved in organizing this thing. There were a lot of people that made this happen, including everyone who's here today, and I see a ton of people, which is fantastic. So hopefully we'll see you at the next TopoInVis, but otherwise have a great IEEE Viz.